start.
Is it?
So, during the previous talk, we have been presented with a two-sided display calculus for a semantic extension of the non-associative Lambek calculus. Now, this, like ordinary sequent calculi, it satisfies a local subformula property. However, when trying to conduct vector chain and cut-free proof search, one is typically confronted with choices that are inessential to the method of setting provability. Now, this problem seemingly being inherent to the sequentialization of rule applications, Girard's reaction was to come up with a kind of parallel syntax for proofs called proof-nets. Now, here I will be interested in an alternative proposal by Andreoli, also referred to as focalization and focused proof search. The idea here is to stick with sequent derivations, but to come up with a method of finding canonical representatives for derivations differing only by trivial rule permutations. My agenda for this talk is as follows. First, I intend to come up with a kind of with a conception of focused proofs or normal form proofs for the Lambek-Grishin calculus. Second, I intend to demonstrate normalization in the sense that every provable sequent has in fact a focused proof. The latter aim I intend to realize using a semantic argument. In particular, I will construct a kind of syntactic model from which normalization results by composing soundness for unfocused proofs with completeness for focused or normal form proofs. Alright, so let me start again with a very brief recapitulation of the Lambek-Grishin calculus. So, defined algebraically, derivations characterize inequalities between formulas. We have the usual three-order axioms on derivability. We have the, hopefully by now familiar residuation and coresiduation laws. However, in contrast with the previous talk, I will not be concerned with the Grishin interactions, but will take into consideration the additive conjunction and additive disjunction, for the simple reason that they tend to make life more difficult when doing focused proof search, hence more interesting. So, I will now continue by discussing focused proofs for the Lambek-Grishin calculus, but to this end let me start by discussing the kind of objects manipulated by proofs or derivations, that is to say sequence. Now, a defining characteristic for the Lambek-Grishin calculus is its symmetry, in particular the existence of an involution on formulas that manifests as error or order reversal at the level of derivability. I have extended this duality to the level of atomic propositions in the sense that for each atomic proposition or atom I also have at my disposal its negation. I've done this for two reasons. First, atoms and their negations actually show dual behavior with respect to focused or normal form proofs. Second, it allows us to define one-sided sequence, thus bringing the presentation of the Lambek-Grishin calculus closer to something like the Grote and Lamarche's work on classical non-associative Lambek calculus. So, sequence then are pairs of structures. I always write them left-sided so as to be suggestive of an intuitionistic interpretation, like with the double negation translation seen during the previous lecture. So the structures occurring in sequence are constructed using three structural connectives, one representing a multiplicative conjunction and disjunction, the other two representing implications or co-applications. More specifically, a sequent is always ambiguous between two dual inequalities, depending on which of the structures is taken to be the antecedent of said inequality and which is taken to be the consequent. Now, what I'm defining here is, you might say, a kind of focused display calculus. And what sets display calculi apart from ordinary sequent calculi is the existence of structural rules that allow one to isolate a name formula prior to the application of the corresponding local inference. So we've already seen such display postulates during the previous lectures and during the previous lecture in two-sided setting. New, you might say, here is the leftmost rule, although already familiar from work by the Grote and Lamarche, which is evidently justified by the ambiguous interpretation of sequence. So to show a little example of the display postulates in action. We isolate some formula A from among structures gamma, delta, and theta. The dual interpretations in terms of algebraic derivations are shown on the side, and it is easy to see that the display postulates map into residuation and co-residuation. So, up to this point, you might say that what I have been talking about is, well, might be mistaken for discussion on any kind of display calculus. What I'm interested in are focused proofs. However, focalization doesn't really show until one starts to look at the logical rules. So I will be considering two types of logical rules depending on the polarity of the main formula. Now, it's easy to see that those formulas considered positive are actually dual with respect to those considered negative and by positivity, vice versa. The difference at the level of the difference with respect to the proof theoretic behavior is as follows. First, those sort of positive inferences, in other words, the inferences targeting positive main formulas, are always invertible in the sense of preserving provability of the conclusion inside the premises. Now, with a focused proof, a normal form proof, you will always try to, so from a backward chaining perspective, where one tries to prove the sequent by working backwards towards the axioms, one will always try to apply the positive inferences as soon as possible. The intuition being that if one is trying to settle provability, a positive step is always the safer path. In contrast, negative inferences are not always invertible. However, to decrease the number of permutations between rules that decrease the number of permutations between rules that involve disjoint active and main formulas, we add a kind of commitment to the choice of a main formula. In the sense that if you choose a main formula, you focus upon it by fixing the next couple of subsequent rule applications, again looking backwards towards the axioms, to the subformulas of the current main formula that we chose. So we try to stick with a given main formula for as long as possible. Finally, my presentation will be syntactic in the sense that neighboring inference steps that involve main formulas of the same polarity will always be collapsed into a single inference step. As a result, we obtain derivations where positive and negative inference is always strictly alternate. Now, I will pursue the following intuition when it comes to defining logical inferences. Logical inferences will always be calculated in advance of proof search from using as a basis the formulas found in the goal sequence, the sequence we're trying to prove. So what constitutes a valid logical inference then is made subject to derivability in a kind of higher order sequent calculus, involving pairs of, on the one hand, a finite set of sequence considered the premises of a logical inference, and a single sequence considered the conclusion. Now, derivability in this higher order calculus is two base cases. The first one tells us that the usual logical axioms indeed constitute inference rules. The second characterizes positive inferences. So the idea is roughly as follows. If we have a positive main formula P, then we introduce a premise for each structure found in some set that we calculate by induction over this positive main formula. Now, it is easy to see that this set is pretty much determined up to the first immediate negative subformulas, and moreover, this set is always a singleton if and only if we encounter no additives. So, you will see all of this in action with a few simple examples in a couple of slides. But first, what constitutes a negative inference is characterized by remaining rules of the higher order calculus. So, to give a simple example, suppose that we have computed rules with main formulas A and B, and we may combine their premises into a rule with a main formula A plus B. So similarly, each negative connective has its own rule with the higher order sequent calculus. There are then, of course, being two rules for the additive conjunction corresponding to the projections. And that pretty much defines the higher order calculus. So there's one more thing to note. I already mentioned that we always try to apply positive steps as soon as possible. And this is, given its formal status with this higher order calculus, by considering positive inference steps as the base cases for derivability. What this all means in practice is that we can actually restrict to sequence containing no non-atomic positive formulas, in the sense that positive inference steps will always be absorbed or compiled away into the negative inferences. This does introduce a few slight complications in the relation between inequalities and focus sequence, but I will return to this later. For now, let me depart from the realm of the abstract and consider something a little more concrete. So, we have here two very simple sequences differing only by the polarizations of the atoms. So, whether they are non-negated or whether they are negated. Now, in a normal or normal display of sequent calculus, one would assume both sequences to have two derivations, depending on which of the non-atomic formulas is decomposed first. However, both sequences will have only a single focused proof, but the shape of this proof actually depends on the polarities of the atoms. So we proceed as follows. First, we calculate our logical inference rules using the higher order calculus from the previous slide, using as a basis the formulas encountered in the goal sequence. And then, we try to prove the sequence. So, starting with the first one, you have little choice but to first decompose the leftmost non-atomic formula using rule 2. Now, I'm using here a bit of an abbreviation. I have marked the main formula with an asterisk, it implicitly being understood that one first applies a couple of discipline postulates to isolate it, but for reasons of space I have not explicitly mentioned these discipline postulates. After that we have little choice but apply rule 3, decompose the other non-atomic formula and we're done. Whereas for the other sequence we have little choice but to first decompose the rightmost non-atomic formula, followed by the remaining leftmost one. So again, here we see that both sequences have only a single focus proof, but focus proofs, the shape of focus proofs tends to be influenced by the polarities assigned to the atoms. Now, another slightly more complex example, although not too complex. We have here a sequence with nested implications. So again, we start by computing the rules of inference from the higher order calculus. Focus proof search here actually terminates with two derivations. We may first decompose the rightmost non-atomic formula using rule 2, fixing the remainder of the derivation by applications of rules 3 and 4, or we may first start by decomposing the leftmost non-atomic formula using rule 3, fixing the remainder of the derivation by applications of rules 2 and 4. Now it should be noted that this permutation of rules 2 and 3 is actually not innocent, in the sense that they give rise to different action matchings. This does mean a kind of non-determinism that we actually wish to keep, that we would consider meaningful. Okay, so here with this I conclude the discussion of the shape of focus proofs, the Lambek-Grishin calculus, and turn to normalization. So the idea again here being to define a kind of syntactic model with normalization resulting from soundness of unfocused proof search. Here understood by algebraic derivations, with completeness for focused proofs. Now I will present these syntactic models on the slides in a manner that is to be suggestive of a more general conception of such models. But I here stick to the concrete case of syntactic models, if only to keep things to the point. So we're working with phase models, having found originating in the Girard's vertical linear logic. So a syntactic phase space, which is much like the frames familiar from Kripke-style semantics, is simply put determined by the set of structures referred to by phases and the binary relation of provability. Formulas will be interpreted by sets of such phases that are to be closed with respect to some closure operator induced by a Galois connection, mapping sets E of phases of structures to the set of those structures gamma that stand in the provability relation with respect to all delta found in E. Well, it pretty much works. Might look a little abstract at first, but it works. So, more specifically, I will be interpreting formulas by pairs of such closed sets, also referred to by facts. Now, it is easy to go back and forth between the current exposition of the interpretation of formulas and that found in the usual literature on phase spaces and linear logic, although the current exposition has the benefit that it reinforces the symmetry behind the Lambek-Grishin calculus, and it tends to ease the formulation and proof of the completeness theorem. Furthermore, it should be noted that this idea of interpreting formulas by pairs of sets is actually inspired by work on the two-sorted Kripke semantics that one may find in the works of Bimbo, Dunn, and Geerke. Now, in looking at the interpretation of formulas, the only cases that I wish to emphasize here are the interpretations of atomic propositions, which are the sets of those structures that actually stand to the provability relation with respect to these atomic propositions. Now, putting surplus of unfocused proof search at this point is just a simple induction on the structure of algebraic derivations. So again, the non-normal form derivations, unfocused proof search are here considered to be algebraic derivations. One may also first define a regular one-sided display calculus, but well, I'm trying to keep things to the point in my presentation of only 20 minutes. Of course, the real work is done in proving completeness. So, keeping it simple at first, one will first want to prove the properties 1 and 2 mentioned as the key lemma for every arbitrary formula A in structure gamma. Now, in stating completeness, recall that I have restricted to sequence containing no monatomic positive formulas, seeing as inference rules for positive formulas will compare later to those for negative formulas. However, this has the consequence that there are inequalities which do not relate to a unique focused sequent, but rather to a non-singleton set of sequence. Think in particular of inequalities which have additive disjunction in the antecedent and additive conjunction in their consequent. Now, these sets of sequence are simply defined by a straightforward generalization of the formulation of positive inferences. As stated, completeness is then easily shown using a composition of the properties 1 and 2 in the key lemma. So actually returning to this key lemma, it turns out that in practice it is actually also helpful to consider to do dual properties 3 and 4. It being the case that it is simpler to show properties 1 and 2 for negative formulas, these then actually implying properties 3 and 4, whereas it is easy to show properties 3 and 4 for positive formulas, these then implying properties 1 and 2. There's one more complication actually. As stated, it's still not quite possible, at least not to me, to prove the key lemma. One will want to consider slight complications of statements 2 and 4, which actually have these simple statements as implications. Now it should be clear at this point, I hope, that pretty much all of the work goes into proving this key lemma, although I will here suffice by mentioning its, by sketching its relevance to the proof of the completeness theorem. So that actually pretty much concludes my discussion. It is of course based on an article that I've been working on. So the full version of this article includes first of all coverage of the classical non-associative Lambek calculus, my reasons for defining defining one-sided sequence for the Lambek-Grishin calculus simply being to bring it closer to the presentation of CNL, thus allowing me to provide a uniform proof of normalization for both systems. Second, well, the non-normal form, one-sided display or sequent calculi are defined as an intermediate step. I have already made a point out of calculating logical rules in advance of proof search on the basis of formulas found in the goal sequence. So this is lent its formal status in the article by defining all the relevant concepts for focused proof search with respect to a finite set of formulas. It's an intended instantiation being the formulas encountered in the goal sequence. And finally, I forgot to mention this, display posits like positive inferences are actually absorbed by the negative inferences, so that we have no need for them anymore. And that is all I have to say for now. Thank you for your attention.
Time for some questions. So I think everybody believes you.
All wants to
Almost go for lunch.
yes, I think that's it.
Good. Okay, well thanks very much. And thanks to all the speakers this morning for staying on time, making my job easy. So we'll break for lunch now and we reassemble here at 2:30.